Recent mathematical modeling suggests that time travel to the past may be theoretically possible without causing paradoxes. The possibility of traveling back in time has long been considered impossible due to causality violations, exemplified by the famous grandfather paradox. If one were to travel back in time and prevent their grandfather's birth, it would create an unresolvable loop. Researchers explored the mathematical aspects of time travel and discovered a way to model time travel without paradoxes. Their findings propose that time travel to the past could be theoretically feasible without causing inconsistencies. In essence, events would adjust themselves to align with the actions of the time traveler, avoiding any paradoxes. For example, attempting to prevent the spread of COVID-19's patient zero might not alter the course of events. Instead, the pandemic would find another path to unfold. While this research remains rooted in mathematics rather than practical physics, it raises intriguing questions about the fundamental nature of time and the possibility of time travel without violating the laws of causality. The quest for a unified theory that reconciles traditional dynamics with Einstein's theory of relativity continues to be a fundamental pursuit in the field of physics. Although paradox-free time travel remains a theoretical concept, it offers a tantalizing glimpse into the mysteries of our universe's underlying laws. Their study was published in the journal Classical and Quantum Gravity.
An attosecond is an extremely short unit of time that equals to 1/quintillionth of a second. There are as many attoseconds in 1 second as there are seconds in the age of the universe. In the past, scientists used femtosecond light pulses to study the motion of heavier and slower-moving atomic nuclei. Each femtosecond consists of 1,000 attoseconds. Making measurements in femtoseconds made it difficult for scientists to observe the movement on the electron scale until they switched to attosecond light pulses. At its core, attosecond physics focuses on electrons, which are tiny charged particles that orbit the nucleus of an atom. With the precision of attosecond lasers, researchers can observe and control electron motion, offering new scientific possibilities. These ultra-short bursts of laser light act like high-speed cameras, freezing ultra-fast processes in time. This has enabled scientists to investigate processes such as the real-time breaking of chemical bonds, giving a detailed look at the rapid changes electrons undergo during these events. The technology can enhance electronics by understanding and manipulating electron flow in semiconductors, leading to faster and more efficient devices. Attosecond techniques can also be adapted for medical imaging, offering unprecedented resolution and insights into biological processes at the molecular scale.
Scientists have created a clock so accurate it won't lose time for 40 million years. It is 1,000 times more precise than any other commercial system. The clock is known as the cryogenic sapphire oscillator, or sapphire clock. It is the result of more than 2 decades of pioneering research. It is so precise it gains or loses only 1 second over 40 million years. An atomic clock is a precision clock that depends on an electrical oscillator, which is regulated by the natural vibration frequencies of an atomic system. Atomic clocks keep time better than any other clock. They even keep time better than the rotation of the Earth and the movement of the stars. Without atomic clocks, GPS navigation and the internet would be impossible, and the position of the planets wouldn't be known with enough accuracy for space probes and landers to be launched and monitored. Atomic clocks are not radioactive because they do not rely on atomic decay. Instead, they have an oscillating mass and spring like an ordinary clock. There are different types of atomic clocks, but all of them follow the same basic principle. The major difference is associated with the element used and the means of detecting when the energy level changes. There's the cesium atomic clock, the hydrogen atomic clock, and the rubidium atomic clock.